In this video, we would write the code for the callback to create an API IK-FK seamless solution. The first thing we are going to do for this video is we will grab the wheelpi script which we wrote in the custom node video tutorial, and we would start modifying it so that we can create a standard custom node inside which we will embed our callbacks. So I have opened here the wheelpi script and I would start modifying it. The first thing I will do is, instead of wheel node, I would call it cvgk node. And here the class name is wheel node and all the attributes are wheel node as well. And I will replace all the keywords with cvg. So all the wheel node words will be replaced by cvg. Okay, the third thing is I will empty out the compute function, because in this custom node we are not performing any computation. So I would just enter pass. I'm not giving any instruction inside the compute function. Later, as I don't need any attribute and I don't need to design any circuitry as well, I would clean up the node initializer function. So I have emptied out the compute function and node initializer function. I will also add author's name and the version number of this plugin, because we have started doing that in last few videos. Okay, so we are all set with creating a custom node. I will copy this and I will paste it in the script editor of Maya. And just for the verification of the code, I would save it and try to load it as a custom node. I'm saving script and I want to save it under C drive plugin folder, and I would save it as custom node.py. Save. And I would go back here and I would load the same saved file. And I will create a CVG node. So it has created the node. However, it's an unknown type node because we did not define that it's a k dependent node. So that's fine. We would not receive any error. It's just a warning. Now we would start adding the code for our callback. And we also don't need these M objects because we removed all the attributes. We would be creating some M objects for the callbacks, but we don't need it from the previous node. Okay. After importing the modified wheelpi script, I would create an array and I will call it ID callback. And here we will maintain all the IDs of the callback whichever we are creating, so that whenever we want to remove those callbacks using these IDs, we can remove them. So I have created an array of, and I have called them ID callback. I would just clean up the script editor. And if we create a simple 3-joint IK setup, so we have 3 joints in the scene and we have attached an IK handle with those joints. And if we take a look at the hypergraph of this structure, we would find that we have 3 joints, 1 IK handle, its effector, the pole vector, and the curve. And we also have the IK solver. When we will be switching between IK and FK using our code, we will need to maintain, or we will need to know the information of all these 3 joints: IK effector IK, handle, and pole vector and pole vector control. So we almost need everything in this hypergraph besides the solver, because the solver is for Maya computation. We don't need it for our node. So we would create an appropriate object to store all these information which we just saw. So I would go ahead and start adding the mObject handles so that we can store their handles, and whenever we need them we can grab the information. So first thing I would add is joint 1, which would be openMaya.mObject type. In the similar way, I would create a joint 2 and joint 3. After that, I would create a active effector mObject. And in the similar way, I would have to create active handle. It would be for IK handle. And I'm calling them active because there is a possibility that we might have more than 3 joint IK system in the scene, so that you have IK for left hand, IK for right hand, IK for leg, left leg, right leg. So active is the one which we are working on, which we have selected. So that's why I'm calling all those variables active. And after that, I would add active pole vector. And active pole vector control. So we have 4, 5, 6, 7 variables or 7 mObject, and in this setup we have 1, 2, 3, 4, 5, 6, 7. So we are done creating our mObjects, and now we would create our callbacks. We would create our callbacks inside the constructor of this class, because whenever we would create this node, we want to create those callbacks. And as we discussed, we will be adding 2 types of callbacks. One will be event callback, which will track the change in selection in the scene for us, and another would be dependency graph callback, and which will track the addition and or deletion of the dependency graph node. So first we would create our event callback, and the way we will create it is using mEvent message class. And to add the event callback, we will use a function add event callback. And this function will take 2 arguments or 2 parameters, which will be what to execute and when to execute. So what to execute is self.callback function. I have not declared this function yet, but we will soon. And when to execute this function? Whenever there is a change in the selection, and the name of the event for that is selection changed. So here, that is how we create our event callback. But as we mentioned that we will be maintaining all the callback IDs inside this ID callback array. So whenever we execute this command, an ID of the callback will be returned. and using that ID we will be able to delete this callback. We will always have to maintain these IDs, otherwise they would float all over the background of your Maya and it would start lagging. So we would say id callback dot append, and we would take the ID returned by this command. Second step is to create a callback which will maintain or which would track the deletion of the dependency graph node. For that, we will create openmaya.mdg message. So this is the class we will be using for creating dependency graph callbacks. And the function which we will use to create a callback which will track the deletion of the node is add node removed callback. And this will also take two parameters. This function itself explains that when to execute, and we know that whenever a node is removed, a function will be executed. So we would definitely have to provide that function, and that function will be self.remove. And second argument will define that self.remove function will be executed when certain type of nodes will be removed, and those certain type of nodes will be depend nodes. So whenever a dependency node will be removed from Maya, self.remove will be executed. And we also append the ID generated by this function inside ID callback. So now we have created our callbacks. I will also indent it properly. So the second step is to create the callback function. And the first argument will be self, and the second argument will be star args, because as a general practice we will always add the star args in the functions which will be called by the callbacks, because certain arguments are also passed to these functions when they are called or executed. So I will provide it two arguments, self and star arg, and for now I will just print callback function. Secondly, I would define my remove function, and in the similar way I will also pass star args to this. Now we would have to consider one thing here, that this remove function will be called when any dependency node will be removed from the Maya scene. It doesn't matter that if it is a dependency node which we created or any other node, and we don't want that. We want to deactivate or kill our callbacks only when our dependency node is removed from the Maya scene. And to do that, we will put a try and except condition, and try will be check if our node exists in the scene. If not, then remove our callbacks. So I will explain you how we can check the node which we have just created, but before that we would write the code for removing the callbacks, and we would write this code in a generic way. In this example we are just creating two callbacks, but if you are creating a complex callback system, how would you remove all those callbacks? So which is very simple, but we would create a loop which will loop over the length of this ID callback. So for I in X range, length id callback, and I would add self, and inside that loop I would first try to delete event message, and then I will try deleting the mdg message. Open Maya dot event message dot remove callback, and I will provide the ID of the callback which I want to remove. Accept pass. And in the similar way, I would try to remove open Maya dot mdg message dot remove callback. To remove event callbacks, we will have to use the remove callback function coming from event message. In the similar way, to remove the dependency graph callbacks, we will have to use the function remove callback coming from mdg message. And I will provide the callback ID to this. Accept pass. Okay, so now we will see how we can check if the node which we have created exists in the scene or not. And to check that, we will use the selection list. So we will first create a selection list. Secondly, we will grab the handle object handle of our custom node which we are just creating, and then using this handle we will try to add this node inside selection list. The benefit of selection list is can only add those items which exist in your Maya scene. So if this addition will not happen, if we will try to add a node which does not exist in Maya scene, an error will be generated. And we will track this error. So whenever there is an error, that means our node does not exist. And in that case, go ahead and delete our callbacks. So now we would first create our selection list, and then we will add the object of our custom node. So we would create selection list and then use add function. And how we can grab the object handle of our own custom node is by self dot this object. So this function will give us the object handle of the custom node which is created by this class. So using this command, we can verify if our node exists inside the scene or not. And if our node does not exist, then remove the callbacks. So this is our simple callback addition and removal system. And before we write our further code, I will go ahead and save this file as a script and try to load this and see if our callbacks are working or not. So I will save the script under C plugin custom or the callback .py. And I would would try to load our callback.py. I would just restart my Maya so that if we have any custom node already loaded, it would empty that out. So I have restarted Maya, and now we would try to load our plugin and create our node. And we have received an error that global name callback ID is not defined. And the error here is because we did not add self in front of the ID callback, so it did not know where to read this ID callback from, because there is no global ID callback is defined. So let's save the script now, and I would try to unload this plugin and reload it back, and then try creating a function or the node. So our node has been created now, and now we would see if our callbacks are being executed properly or not. So I will clean up the script editor, and as soon as my selection is changed, my callback function is being called. And I would select my node, and then I would go to hypergraph or hypershade, and then I will remove this node, and then I will try selecting and deselecting. I don't see any printout here, so callbacks are not being executed. And I will create the node again and select, deselect, and I can see my printout again. Our callback system is working fine now. The next step is to write the code for switching the IK and FK. For that, I would restart Maya and start writing more code in our script editor. So all the code for switching IK, FK we will be writing inside the callback function. I will not be writing the code here line by line, otherwise it would take 1 more hour to explain everything. And our motive of this video is to create the callback system. However, I would go through each section of the callback function, and I would explain you what it is doing and what we are supposed to do. To perform the auto IK-FK switching, we will be doing 3 different major things. First, we will find out which mode we want to switch to based on what is selected in the scene. Second, we will find the information of all the 7 objects or things of our 3-joint chain IK system. And what are those 7 things? Are these 3 joints: IK handle, effector, pole vector, and the pole vector control. So we will grab the information of all these 7 things so that we can control, or we can find out whenever we need any information. And the third and the last thing is we will perform the operations based on which mode we are at. So if we are in the IK mode, we will perform certain functions or certain operations. and if we are in the FK mode, we will perform certain operations. So majorly, we will be doing these things. So in the script editor, I have pasted the code of the callback function, and in this way we would have our complete script for or the complete plugin for our auto IK-FK switching. And now I would start explaining you what we are doing here in this function. So the first thing is to find out which mode we want to switch to. And our mode is based on what is selected in the scene. So whenever we do anything with the IK, we usually either select the IK, pole vector, or the effector. However, the node effector and the pole vector cannot be selected through the viewport, so majorly a user will be selecting the control curve, pole vector control curve, IK handle, or the joint tree, which is attached to IK effector. And if someone has selected joint 1 or joint 2, we are supposed to be at FK. So for performing that operation, we would first want to find out what is selected in the viewport. We will be using getActiveSelectionList for finding out the active selected objects, and then we would run a selection list iterator through all the objects that are selected. And then in here, I am finding out what exactly is selected. So one by one, this iterator will go through all the selected objects. And then if the selected object's API type string is IK effector, that means IK effector node is selected. Then we will find out if our control curve is selected. And the way we will find out is if we have already grabbed the information for pole vector control, which we have not yet, we will be doing it in the second step when we will find out the information of all 7 things or objects of the IK system. Then we will compare the name of the active pole vector control and the name of the object selected. If their name match, that means we are in the IK mode. That means our pole vector control is selected. And then the third thing, if our joint 3 is selected, and how we would find out if our joint 3 is selected, we would see if to the object which we have selected in the viewport is an IK effector type node is attached to it. If yes, then it is a joint 3, which is the third joint of the joint chain. So here I am finding out the connections of what is selected. And then if one of the connections is KIK effector type, that means we have selected the joint 3 of the chain. And as soon as we find that KIK effector, we would take that information and we will store that in self-active effector. So at this point, this is the active effector. Now we would go back to our blackboard and draw the joint system we have in the Maya scene. By default, we would set our mode to FK, which is right here. So by default, I have set my mode to FK. And then in this code, I'm trying to find at which situation I would have to switch this mode to IK. There can be 3 situations where we will have to switch to IK. First is if our IK handle is selected. Second is your joint 3 is selected. Third is your pole vector control is selected. When we want to switch to FK back, when joint 1 is selected or joint 2 is selected. By defining that, we achieve our first task, which is find out which mode we want to switch to. Now we would move on to our second task. And our second task is to grab the information of all those 7 elements. And here we would start collecting the information. If you know, we have already grabbed the information of one of the elements out of 7 elements, which is active effector. We have grabbed the information of this effector node. Using this effector, we would find out the IK handle, because IK handle is connected to effector node. After finding out the IK handle node, we would find out its attribute. And the attribute which we are going to find out is IK blend. And that's what we need to control. In the later step, we have reached to this point. Now we want to jump to this node, which is a pole vector. So after finding out the IK handle, we will find out the IK pole vector constraint, and using which we will find out the pole vector control. And that's what I am doing here, is finding the pole vector constraint, and when I find the pole vector constraint, find the pole vector controller curve. In this way, I would have information of 1, 2, 3, 4. 4 elements. I still have to find the information of 3 more elements, which are our joint 1, joint 2, and joint 3. And we will use the information of these 4 nodes to grab the information of these 3 nodes. And how we will be able to do it? We know that effector node is connected to a joint, which is joint 3. And here I am finding out the information of nodes connected to the effector node, active effector node, and the joint which is connected to effector node is our joint 3. Similarly, our IK handle is connected to joint 1. So the joints which are connected to the IK handle, we will find those out, and the joint found is the joint 1. So here I am finding out the joint 1 using our active handle, which is IK handle. Now, the only node which is left is joint 2, and we know that it is connected to joint 3 and joint 1. But in a complex skeletal system, there might be several other joints which might be connected to joint 3 and joint 1. So the trick here is we will find out all the joints for joint 1 which are connected to its scale attribute. So if we would see the connection bridge, it is joint 1 scale is connected to joint 2 inverse scale, and joint 3 is, this bridge is joint 2 scale to joint 3 inverse scale. So first we would find out all the joints that are connected to the scale attribute of joint 1, and then we will find out all the joints that are connected to the inverse scale attribute of joint 3. And if the name in these two sets matches, that means that joint is joint 2. So that is what I am doing here. I am finding out all the connections that are connected to the scale attribute of joint 1, and I am storing it in a mplug array. And after that, I am finding out all the connections of the joint 3 that are connected to inverse scale attribute of the joint 3. And then I am matching the sets, and if any name in that set is equal, that means that is our joint 2. So in this way we have achieved our second goal of finding the information of all 7 things. In the blackboard, I will explain this simpler diagram of these 7 elements. So here is a simpler version of these 7 nodes which we just saw in Maya scene. Now it's the time to perform our third operation, which is performing certain functions or operation based on the mode we are at. Now if we are in mode FK, forward kinematics, in that case we want to first set the IK blend plug or attribute to 0, and as soon as it's 0, that means we are in FK mode. Second thing is we would set the visibility of pole vector control to 0, because in the FK mode we don't need the pole vector control. And if we are in mode IK, in that case we want to set IK blend attribute to 1. That means it's the IK mode for the IK handle. Second, we also want to snap the pole vector control to joint 2, so that we don't see any snapping when the system would auto switch IK FK. Everything should stay intact. So that's why we would need to snap the pole vector control to joint 2. That is what we are doing in the function. You can do a couple of more things. You can set all the attributes of IK handle to non-keyable, so that when we select the IK handle and the joint, we don't key the attributes of the IK handle. And you can also hide the IK blend attribute from channel box, and you can also set it non-keyable. And the fourth thing is definitely very optional, that if you don't want to directly snap your pole vector over the joint 2, You can add some translation. Now I will go ahead and save my script and load that as a plugin in Maya and test it in the IK system. Now we would see how to create a simple 3-joint IK system and apply the pole vector and IK handle to it, and then start animating it using our technique. So first I would create 3 joints, and I apply a IK handle to it. So we have the IK handle. And now the third thing we are going to do is apply a pole vector. I would select the curve, nerve circle curve, and then I will select the handle and I will put or apply a pole vector constraint. So we have our pole vector and IK handle. I would rename that as pole vector control. Okay. Now I would apply the handles, the control handles to joint 1, joint 2, and joint 3, because when you will be giving this rig to the animators, they would not be grabbing the joints, they would be grabbing the controllers. So I would create a nerve circle 1 and I will duplicate that twice. So I have 3 nerves circles, and I would snap the circle 1 to joint 1, nerve circle 2 to joint 2, and nerve circle 3 to joint 3. And now I would run a trick. I would execute these 3 commands, and what they would do is they would parent the shape node of nerve circle inside the transform node of joint 1. So I would parent the nerve circle shape 1 to joint 1, and you can see that the transform node of nerve circle 1 is now empty. So I would delete that, and the nerve shape is inside joint 1. And I would do the same thing for nerve circle shape 2. And I would delete the nerve circle 2 transform node. And for the third nerve circle, I would parent it to the IK handle. So when I would grab this, I will be grabbing IK handle. So we have our system ready. I can grab this and move the joints. Now I would import or load my plugin and create our callback system node. And I would test if it is working or not. And yes, it is working. So now I would start animating this system. I will first go to frame 1 and select joint 1 and joint 2 and key all the attributes of these 2 nodes. And then I will go to frame 20 and then I will rotate joint 1 and key it, then rotate joint 2 and key it. Then I will go towards or at frame 30, and this time I would grab my IK handle and I will move it, and keeping this as a selection, I will select joint 2 and joint 1 and I will key it. So it looks weird for a second, but as soon as you change your selection, it's fine. And here is your animation which you have just done. So the trick is, when you will be keying the joints, you will always be keying joint 1 and joint 2. You might have to keep IK as a selection to keep it in IK mode, but eventually you will always be keying joint 1 and joint 2. So that's how you will be keying and animating this IK system, which is a seamless IK-FK, and that's why I call it IFK. It's an inverse forward kinematics. So that is how we use and we create our 3-chain joint IFK system. And I hope that now you would be able to create your own skeleton and apply those nodes and callback systems. And I hope that now you can create your own IFK 3-joint chain system. And I hope that now you can create your own 3-joint IFK system and apply to your rigs. And that's it for now. Thank you.